Now, melting and vaporizing are physical changes, but the idea is also applicable to chemical reactions when there's actually a chemical change. The first thing that happens when chemical change takes place is the bonds between the atoms and the reactants break. When bonds break, attractive particles are pulled apart. So you think about this reaction here. This is methane, where carbon is bonded to hydrogen, and these are two oxygens, where oxygen is bonded to oxygen. All these bonds are going to get broken. That'll be broken, that bond, that one, that bond, that bond, and that bond are broken. And those attractive particles are going to be pulled apart from each other. That takes energy. That's an energy input. Here's what it might look like if we could see on the atomic scale. We have now broken the bonds and pulled all those attractive particles apart from each other. That took energy. This is an energy in process. That's endothermic. The next thing that's going to happen is these particles are all going to reorganize themselves into new molecules, the product molecules. When the bonds form, attractive particles are brought back together, and that releases energy. Here's what that might look like. Now, with the bonds having reformed here and here, here and here, here and here, what we've seen is a large amount of energy was released during that product formation. So it takes energy to go in to make the reactants break up, but then energy is released back out when the products form. The energy that you had to put in to break the bonds was bigger than the energy that was released. Then you have a delta H for the reaction that's positive, and we call that an endothermic reaction. More energy went in than went out. If, on the other hand, the energy input was less than how much got released, well, that means change in enthalpy for the reaction is negative, and that's what we call an exothermic reaction. In other words, more energy went out than went in. Here's an example problem. You're combusting some propane, C3H8. 2220.1 kilojoules are released for every mole of propane combusted. Say 10 grams of propane are combusted. How much energy is released? Well, here's what we know. We know that 10 grams of propane, C3H8, are reacting. What we want to find is how much energy is released, like maybe kilojoules. How can we convert? Well, I know something about how much energy is released per mole, so I think I'll first change this to moles. I know the molar mass of propane is 44.097 grams per mole. So by multiplying by this factor, I get rid of grams and I have moles of propane. But the problem tells me that 2220.1 kilojoules are released every time 1 mole of propane burns. So now I get rid of moles of propane, and my answer has kilojoules in it, which is what I want. I should have 3 significant figures in my answer. When I do my arithmetic, it's 503 kilojoules. Okay, you try this one. In the combustion of octane, C8H18, 5,508.1 kilojoules are released for every mole that burns. How many grams of octane would you need to burn to provide 30 megajoules of energy? And just a little reminder, a megajoule is a million joules. Okay, here's how you can figure this out. Now we're given energy to start with, 30 megajoules in particular. What we want to know from this is ultimately how many grams of octane, C8H18, have to combust. Well, the only fact that I'm given here is that 5,508.1 kilojoules are released for every mole of octane that's burned. So I want to get this into kilojoules, first of all, and then somehow turn that into octane, using things that I know. So I know that there are 10 to the 6th, or a million joules in every megajoule. So that'll convert me into joules and get rid of megajoules. But I'm really going to want kilojoules here, so I know that there are 1,000 joules in a kilojoule, and that'll get rid of joules and get me kilojoules. Here's why that's useful, because it told me that 5,508.1 kilojoules is the amount released every time 1 mole of C8H18 burns. So now I'm done with energy. I got rid of that, and now I'm in matter, moles of octane. But I want grams of octane, so I'm going to multiply by the molar mass of octane. 1 mole of octane has a mass of 114.232 grams. Moles drop out, and I'll have grams of octane, which is what I want. Now I do my calculation. I've got 2 significant figures. The answer is 600, so I write it this way. 6.0 times 10 to the 2 grams of octane. All right, this is a more challenging problem. I want you to read through this, stop the video, read through this problem, and do your very best to solve this thing. I'm not going to give you an answer. I want you to figure this out. Come and see me with your answer, and I'll let you know if it's right. And if you didn't get it right, I'll give you some hints. Or if you just couldn't get it done, I'll give you some hints. It's important to work your way through a problem that's this difficult, because that's how you'll know that you really understand.